An introduction to Energy Star for Homes version 3, a peek behind the scenes, checking out what's new, going over 3.1, 3, and then the upcoming revision 8. This course is approved for 1 hour in continuing ed, GVCI, AIA, HSW, AIBD, NARI Green, certified green professionals, and may be applicable to your state or design contractor license. My name is Brett Little. I'm the executive director here. I'll be your moderator today. Green Home Institute is the organization hosting this session, and we're a nonprofit with a mission to empower people to make healthier and more sustainable choices in the renovation and construction of the places we live. We couldn't do it without their support. Anderson Windows, huge supporter of us. Panasonic Ventilation, check them out, as well as our members, volunteers, board of directors, and our partners throughout the U.S. Do you support greener homes, support these sessions, help keep them free, become a member today, and get discounts on other training, education, and green certification fees. All right, so with that, I'm going to hand it off to and introduce our presenter, Rick Gazika. He has over 12 years of experience in residential new construction. During his time with ICF International, he has led the account management of the Energy Star Certified Homes program on behalf of the EPA. He also launched 5 separate new homes programs on behalf of utilities in Maryland, 1 in Pennsylvania, and 1 in North Carolina. Prior to his work at ICF, he worked at NVR as a project and costing manager in Virginia and Pennsylvania. He's built over 200 homes and is responsible for $2 million of projects on an annual basis. So Rick, go ahead and take it away, and thanks for being with us here today.
Thanks, Brett. Appreciate the opportunity to speak with everybody. All right, so I'm going to give you guys a presentation about Energy Star, and we're going to walk through here today. Hopefully, as Brett said, if there's anything that pops up that you have a question about, please set it in the question box, and we will get to it at the end. Oftentimes, we find when we do these presentations that the questions are actually answered later on. So the agenda today, I'm going to talk a little bit about why Energy Star, and then go over sort of step-by-step how we came through to have revision 8 and version 3.1 come into being, and then sort of get into the nitty-gritty details about the thermal enclosure system, HVAC systems, and water management systems that are associated with all Energy Star homes. At the end, we'll leave it open for Q&A and wrap up from there. So, learning objectives for today, gaining understanding, hopefully for the Energy Star version 3 and 3.1 requirements. Learn about some of the program updates that we've released over the last year that ensures value-added features and performance for the Energy Star homes. Learn about how to become an Energy Star partner and access resources to successfully promote the program within your market. And then, like I said, we'll get into the weeds and discuss Energy Star on the technical side, details associated with both thermal enclosure and HVAC systems. So, first question, what is Energy Star? So Energy Star has been around for over 20 years, practically forever when it comes to energy efficiency programs. In addition to homes, it identifies the most efficient products, buildings, and plants, and it's all based on the latest government-backed standards and verified by a rigorous third-party certification process. And of course, it certifies tens of thousands of new homes across the nation each year. So last year in 2015, we did over 80,000 Energy Star certified homes in the country. And that's actually put us over 1.5 million homes since the beginning of the program, which was launched 20 years ago back in 1996. So that's nationwide. And, you know, another benefit to Energy Star is the recognition. So sort of as a result of this private-public partnership, the awareness for the Energy Star brand now exceeds 85%, and the preference for Energy Star grows each year. So that's a sky-high number. It's really high. I mean, there's not many things that 85% of Americans are aware of. You know, they're leading a lot of busy lives, and there's obviously a lot of competition for their attention. So for this program to have such a high recognition really speaks greatly about the partners who have promoted it and the consumers who have found value in it. So one of the key success of Energy Star across the entire portfolio is trying to reduce the complexity of energy efficiency to one simple choice. So everybody on the phone here knows there's actually quite a bit that goes into making a home more efficient, talking about installation of insulation, proper HVAC design and commissioning, blower door tests, duct blaster tests, and on. But to a typical home buyer, or even to my wife, there's so many other things to consider, like curb appeal, the price of the house, the location, the school district, the granite countertops. What Energy Star provides is an option for a simple choice. Energy Star tells the homeowner with one glance whether or not the home is efficient. So when we think through it, there's sort of 5 key ways where we think Energy Star adds value. The first is the branding. Energy Star provides a brand, like we said, is recognizable by 85% of the market. A tried and true system-based approach, so enhancing efficiency and comfort, allowing you to promote your product better. Code preparations for energy performance requirements. So as many of you know, codes have ramped up here over the past decade. Energy Star has stayed ahead of codes and has helped prepare builders and raters in advance of the adoption of these new codes. Energy Star also provides risk mitigation, so reduced callbacks and the chance of litigation, and finally cost controls. So even though Energy Star itself might have some more cost up front to certify the home, we believe these costs outweigh, we believe the value outweighs these costs. So if I'm talking about cost benefit, we get this question pretty often. It might be one I said in the box already. What is the cost to build an Energy Star home? And in true Washington, D.C. fashion, the answer is really easy. It depends. So it depends on where the builder is starting from, what market they're in, and what measure they select. But it might not be as much as you think. So EPA has done analysis, and the most recent cost and saving document says that for a 2,400 square foot house, the cost would be between $2,000 and $2,500 more to build the house rather than to 2009 IACC. Most of those costs are actually associated with hitting the HERS index target. So that would be investing in the amount to get just a HERS rating and to get that score low enough. The next big bucket of cost is the verification. So Energy Star does require third-party verification on site, and their cost is set based upon what the local market dictates. So even though it's a little bit more cost to certify a home, the certified home will provide the long-term value in the form of reduced utility bills and maintenance needs and improved resident comfort. So studies show, and I don't have the documentation right now in front of me, but homes, over 86% of consumers care about the environment, and the majority use third-party certifications in their purchasing decisions. So you can think through, third-party and other aspects of your lives that you rely upon to verify that the products are meeting higher standards. They also reveal that energy efficiency in green homes sell faster, sell for a premium, and have valuation to capture the value of their energy efficient features. So with all that in consideration, the next aspect is, how do I join Energy Star? So the Energy Star does have a formal partnership opportunity for builders, residential developers, home energy raters, and utilities. So if you're looking to get started with a partnership, the best spot to go is to energystar.gov and complete the online partnership agreement. There's a short but mandatory training requirement. It's going to be actually here in the next month, 2 short videos for builders to review that in total add up to about 12 minutes, going over sort of everything that's associated with Energy Star. And then our home integrator graders will have to be trained. Typically the training is packaged in with the HERS rating course that they take. And then to maintain status, your company is required to certify at least one home to Energy Star each year, whether you are a builder or a rater. So, kind of touched upon this earlier, but there's two key components that comprise Energy Star. There's the energy efficiency target, and then there's the mandatory features. So the target is a specific HERS index defined for each home that's meant to be 15% more stringent than code adopted in that state. So for 2009, 15% more efficient for 2012, there's Energy Star version 3.1. The second component is the mandatory features, which ensure that energy efficient targets do not come at the expense of comfort, quality, or durability. So let's discuss the energy efficient target a little bit more. So I said in the last slide, the target was specific to each home, and that's true. But in general, for a version 3 Energy Star home, the HERS index is between 65 and 75. So version 3 is the version that's mostly being enforced across the country right now. Version 3.1 is enforced in states that have adopted either the 2012 or the 2015 IACC, and the target HERS index for those states is between about a 55 and a 65. And nationwide, the average HERS index last year, as reported by ResNet, was a 63. So that means that the average HERS rated home is already meeting one of the two components of our program. So the other component of our program is the mandatory features. And just like we want an Energy Star light bulb to be efficient but also turn on quickly and not make too much noise and also last a long time, we want to make sure that the energy efficiency target for Energy Star is met but not sacrificing other important features like the comfort, durability, and quality. So for that reason, we lock in some certain features that will make a real difference to consumers. So these are captured by the checklists that are associated with Energy Star that we'll get into here in more detail as we go along. For the most part, they address the thermal enclosure system, which we think of as the walls, insulation, and windows, the HVAC system, which includes, your air conditioner, your furnace, and also your ventilation that you're speccing out for the home, and then a water management system. And by water management, we're not talking about the water that goes through the pipes per se, more so preventing water from getting into the house because we're building these homes tighter. So proper flashing around your windows, proper leak screen if you're doing stucco, that sort of things. So I touched upon it briefly before, but so for version 3.1, this target HERS index is more stringent, but despite it being a more stringent target, there's no other mandatory measures in the performance path. So if you don't want to move all of your ducts in an air handler into a conditioned space, that's fine, so long as you compensate with another measure. Or if you don't want to put in a tankless hot water heater, that's fine, as long as you compensate with another measure. The other thing to note is there are no changes to the inspection checklist. So if you're building a house with version 3 and you're using your checklists, the checklists at the top say version 3 or version 3.1. There is no difference. So besides the target HERS index going down, everything else remains the same in terms of the home. So I want to take you on the most recent change to Energy Star, which is revision 8, and especially when it comes to documentation. So I wanted to give you a quick visual tour of how things have changed, and I'll give you some links to sites to follow up in more detail. So first, the Energy Star HVAC quality installation checklist that used to be the contractor checklist used to be a one-page document. It's now been separated into two documents. The first is the HVAC design report, which contains design items related to the house. And the second is the HVAC commissioning checklist, which contains commissioning-related items to the house. So the design report, which can be delivered from RateSoft currently, and we're looking to work with HVAC to have that. Design report is given on a per plan design basis. So if a plan design, similar to a rem rate file, you build out a rem rate file and then use it continuously. The same with this design report. You'll develop an HVAC design report, deliver it over, per plan design and then not have to complete it on a per house basis anymore. The commissioning checklist is still required to be filled out by the HVAC contractor, but the HVAC contractor is going to be the one that holds on to that report moving forward. There's no transfer of information. So in previous revisions, the HERS grader was required to collect that report from the HVAC contractor. It was a pain point and one that was causing not as much value for the HERS grader to review that checklist. So from that point, we've removed that pain point. HVAC contractors are still doing the work. They're still collecting that information, but they're keeping it internally. So on the next slide is the radar inspection checklist. So the thermal enclosure system checklist and the HVAC system radar checklists have also been split into two documents. So there's now a radar design review checklist. Again, this design review checklist is done on a per plan basis. It's just half a page. It's reviewing the design, HVAC design report that's given to the radar, and then also it is, reviewing some other key points that you would do at the design phase, like ensuring that the window values are going to meet the code requirements. The second part of the checklist is the radar field checklist, and that contains all items to be completed in the field. So it's one page front and back, and it's broken down into both the thermal enclosure aspect, but also into the HVAC diagnostic tests that a radar needs to perform. Finally, the water management system builder checklist. Again, we had received a lot of feedback from the field that the delivery of the checklist wasn't bringing any value to the house. So builders still need to ensure that they meet every requirement on this document, but they're no longer using the checklist. They're no longer required to use the checklist to guide them through or pass that off. So as I said before, it's not water in terms of the water that's going through your pipes, making sure that your foundation is properly damp-proofed, making sure that you're managing the water inside to prevent leaks and stuff, so showers and tubs and HVAC drain pans properly installed as well. So summary for sort of each document and how it got broken out. If you are able to click on this link, the EnergyStar.gov New Homes Policy Record, you can see in more detail. But basically, we went from these 4 checklists on revision 7 to only having one checklist for a rater to do on every house, which is the rater field checklist. They're going to do the rater design review checklist on a per plan basis. The commissioning checklist is done for every house by the HVAC contractor but held internally. The design report is done per plan, delivered back to the rater. And then the water management system builder requirements is held internally by the builder. So what we've heard from partners who have started using Revision 8 is that it's really cleaned up the process flow. A lot of this information was given at the end of the house in sort of a fire drill manner. It makes for more certainty for the house to earn Energy Star and alleviates pain points that weren't adding much value to the home. So now that we've sort of talked through the requirements, I wanted to kind of go through the weeds of each part of the house. So to reiterate, complete thermal enclosure system and why Energy Star thinks this is important. Basically, a well-insulated and well-air-sealed home with efficient windows and doors will reduce the amount of energy needed to keep the home comfortable. So a home without a complete thermal enclosure system may not be comfortable regardless of the amount of energy consumed. So I could have a house that's extremely leaky, but if I put in a high-efficiency furnace and a high air conditioner, it could have a good energy performance. The house itself would be comfortable. So the rater field checklist that we talked about earlier, it's the thermal enclosure checklist from before is covered in all 4 sections, and it basically is used to reduce convection, conduction, and radiation. So make sure that we're not allowing those heat sources to come into the house. So the first section of the radar field checklist here is high performance fenestration and insulation. So the two areas where we'd like to highlight here for the windows is the solar heat gain coefficient and the U value. So the solar heat gain coefficient is a number between 0 and 1 that represents the proportion of solar radiation that passes through the window into the home. So in the south, we'd like to see that number much lower in the 0.2 to 0.25 range. In the north, it's not as important. So by eliminating the radiant heat coming into the house, it eliminates the cooling time. And that's great for homes in southern climates. Homes in northern climates, it's not as important because the radiation from the sun in the winter is actually valued in helping to decrease the amount of energy used. The other aspect for the windows is the U value. And so the U value essentially, to get into really technical terms, the coefficient of air-to-air heat transfer for fenestration feet per hour times the square footage times Fahrenheit. Essentially, the easier way to think about it is it's the inverse of the R value. So if you have a window that has a 0.3 U value, you're looking at an R3 for that window. And if you're building a house that has R13 in the walls or R21 in the walls, you know, it's a big gap in terms of the performance. So a window may be high performing at an R3, but compared to the wall itself is not performing very well. And this next picture here shows that. So you can see the image on the left is having insulation that helps decrease the rate of conduction caused by those extreme temperatures. So, you know, you can see that I actually blocked out the windows here. On the left-hand side, we have the quality installed house. The insulation is pretty uniform through the RI camera. On the right-hand side, we have a poorly insulated house. And you can see those extremely bright pieces at the top and the bottom of the wall is where insulation actually wasn't installed. And so we have a wall that's not performing well. The second section of the radar field checklist for the thermal enclosure portion is fully aligned air barriers. So where we're thinking this most commonly occurring is between the bathtub and exterior wall, or a stairwell that's against an exterior wall. When you have drywall on the inside, that acts as an air barrier. But we don't have an opportunity to put drywall up on a wall, and you just have insulation installed. What can happen is the infiltration can go through there and cause cold spots throughout the house. So Section 2 addresses this by sort of detailing out key parts where thermal enclosure systems, the air barriers are often missed in construction practices. Section 3 talks about the reduction of thermal bridging. And so this is a fancy way of saying places where we don't put in insulation because we have studs. So studs typically are poor insulators because they allow extreme temperatures in the outside to conduct right into your home. So a stud has an R value of usually R1 per inch of material. So if you have a 2x4 wall, that means your stud is an R 3.3. So basically the same value as your windows. So the thermal enclosure reduced thermal bridging section is to make sure that we're not over installing wood. So it's asking to, cut down on studs at corners, using California corners there, cut down on studs surrounding windows and doors. Often it's over-engineered, putting too many studs in. There's also the opportunity to use continuous insulation. So if you're using 1/2 inch or 1 inch foam on the outside, you can use that as well to cut down on the thermal bridging that can occur. So Section 4 is air sealing. And so this is another key part, and it works really well with Section 2, which is the air barriers. So whenever we have the opportunity to seal off the air coming into the house, whether it's from the air barriers or filling in holes with caulk or foam, this section calls out key areas where this is overlooked and prevents drafts from coming into a house. So in conclusion for the thermal enclosure system, what it helps builders and raters do is understand how their high-performance home works and how to properly insulate, how to select their windows, calls out areas for the home to be sealed, whether it's through an air barrier or through air sealing with a caulk foam, and then reducing the thermal ridging for improved comfort. So taking out places that used to be studs and putting insulation in its place. So with that being said, I wanted to go into the HVAC system and touch upon the requirements that Energy Star has here. So even if a home isn't going to be Energy Star, even if it's not going to be HERS rating, it's just going to be built to code, which, as we like to say, is the worst possible standard allowed by law. An HVAC designer is still required to calculate the cooling and heating load and select the equipment based on that load. So this isn't just a topic that's relevant for Energy Star homes or high-performance homes. This is something that's supposed to be occurring with every home built in the country. And so Energy Star references ACA and the 3 manuals they have developed to assist with HVAC planning and design. So a properly designed system meets all 5 of the features listed here. So a right-sized heating and cooling system that are quality installed, a whole house fresh air system, effective kitchen and bath fans, an upgraded air filter, and combustion safety features to protect the inhabitants. So to start with first, I want to talk about Manual J. So Manual J walks you through the steps to calculate the peak cooling and heating load, and that's always about the same for a given house. So as we discussed earlier, Manual J was developed by ACA, or the Air Conditioning Contractors America, and the majority of the time we see Manual J done with software to help automate the process. And if you're looking for software that's available, you can definitely go to the ACA website, and it shows the approved software that's there. So heating loads are just like structural loads. So structural loads tell us how many pounds a foundation has to hold up, and a cooling load tells us how many BTUs the cooling equipment needs to remove from the home. So a structural peak load will be the maximum weight that a foundation needs to hold, measured typically in pounds per square inch, or PSI, while the cooling peak load is the maximum numbers of BTUs per hour that need to be removed from the home. So ACA's Manual J is the most common standard for calculating these cooling and heating peak loads. So if the equipment is chosen using a calculated load that's too small than the actual load, the equipment won't be able to keep up and do what it needs to. So if the equipment is chosen using a load that's too large than the actual load on the home, then it will be overkill. So if I have a house that's calculated too low, basically when it gets hotter in the summer, it's not going to keep up, and the house will continue to get warmer and warmer because it can't remove all the BTUs. Now, if I oversize it, what typically will happen here from an energy perspective is that I will be able to cool the house off, but the size of the air conditioner is not just cooling the air, it's also built to remove moisture from the air. And so if it's cooling the house off too fast, the home will still feel clammy to the inhabitants, and rather than being comfortable at 75 or 73 degrees, they'll think that they need to run the air conditioner at a lower temperature. And so they'll continue to push that air conditioner lower until they reach their comfort level, which means that a system that is larger than it's supposed to be will be running for more time than it needs to be because the system was designed improperly. So the 3 challenges when completing load calculations, Energy Star helps overcome. The first challenge is getting the right input. So from an HVAC contractor perspective, garbage in means garbage out. And so that's why Energy Star requires raters to oversee the key inputs for a load calculation. So the raters ensure that the insulation is installed correctly and make sure that the house is air sealed correctly. They actually have the same inputs for raters to do a energy model as HVAC contractors have to do an HVAC model. And the second challenge is getting designers up to speed using the Manual J software and trusting the load calc from that software. And this is going to take time and experience. So Energy Star has been working with a lot of designers across the country that have been doing this for a while, both from the hot dry in the Southwest, the hot humid in the Southeast, and they've all reported back that if you follow Manual J and you have everything that you're putting into Manual J verified, that the process does work. And so Energy Star continues to reach out to builders and raters to make sure that this process is being done. And then the third and final challenge is finding that the inputs in the field are correct. So designers are never paid to do this. HVAC designers don't go out after they install the duct system and make sure that the insulator does his job right and the air sealer does his job right. So there's just too many variables that they don't have control over, and no one else verifies. And this is where the rater and the HVAC contractor can work well together. Because in certifying an Energy Star home, they're able to confirm that all the inputs that are put in are being done by the builder as well. So that's Manual J. The next part of the design process is Manual S. And it would be helpful to think of the heating and cooling equipment as just a BTU machine, so two modes, the on mode and the off mode. And so you probably know that you can get a different size of a BTU machine from a single manufacturer. So manufacturers typically sell their BTU machines from anywhere from 1.5 to 5 tons of capacity, where 1 ton equals 12,000 BTUs. So most of the manufacturers sell machines with capacity that ranges anywhere from 18,000 to 60,000 BTUs per hour. So if a designer picks a 3-ton machine, you'd hope that it would have the capacity of 36,000 BTUs per hour. Unfortunately, it's not that easy. So the capacities that we're talking about are called the nominal capacities. Nominal means in name only. So these capacities are not what you'll actually get when you install the equipment in a home. And this is a key concept and one that Energy Star continues to push forward. So I have a list here of a couple examples to illustrate the point. So we have our BTU machines. The machine is an air conditioner with a nominal capacity of 3 tons at 36,000 BTUs per hour. So let's say we install this a few hours south of Atlanta, Georgia, where the outdoor temperature is 95 degrees. Based on this, the actual capacity of this system is 33,200 BTUs per hour. Now, if I take this same exact piece of equipment and move it over to Tucson, Arizona, where the outdoor temperature is 105 degrees, the capacity of the system actually drops. So it's now 31,400 BTUs. Now, if I take this same system, again, traveling across the country, and put it up in Ithaca, New York, the outdoor temperature there is quite pleasant, around 85 degrees, and the capacity actually increases to 35,800 BTUs. So when a designer picks a BTU machine for a home, its performance is going to depend on where it's installed, or more specifically, what the design conditions are. So in this example, we saw that a single BTU machine, or air conditioner, with a nominal capacity of 3 tons, or 36,000 BTUs per hour, had an actual capacity of anywhere from 31,000 BTUs all the way up to 35,000 BTUs. So the actual capacity is the type that everyone here should really care about, and that's called the design capacity. And it's another key term. So what do I mean by that? Let's think back to the Manual J 3 minutes ago. The cooling peak load was calculated at a very specific set of conditions. So it's 1% cooling temperature and 99% heating temperature. Indoor, it's based upon 75 degrees inside the house with 50% relative humidity. It's under these design conditions where we've calculated the cooling peak load. And in this example, that's 35,000 BTUs per hour. So therefore, we want to pick a machine that has the capacity at those same design conditions. So here's the formal definition of design capacity. the capacity of the equipment at the same design conditions used to calculate the design peak load. So with this in context, we want to walk through the actual steps the designer will take to select a piece of cooling equipment. First, they'll need to gather some critical information from Manual J, but they'll need to get the cooling peak load that came out of Manual J. Let's say it's 27,000 BTUs per hour of sensible load and 2,000 of latent load. They're also going to want to know the indoor design temperature, which is, we'll say, 75 degrees indoor with 50% relative humidity. And finally, they're going to want to know the outdoor design temperature. So for Georgia, with the 1% design temperature, we have as 95 degrees. So now, if you want to just shut your eyes for a second and not be completely overwhelmed, we can see an example of the expanded performance data from a manufacturer's catalog. So you see how this table is laid out. On the left side, we'll see the wet bulb temperature, which is the latent, and for a single measure that accounts for both temperature and humidity level in the air. So for our design conditions, 75-degree indoor air with 50% relative humidity, the wet bulb temperature is 63 degrees. Also on the left, you'll see the fan speed of the indoor unit. So there are 3 settings, low, medium, and high. And when the equipment is installed, the fan can be set to any of these settings. Usually, a designer will aim for the middle speed so they can adjust the speed up and down if something in the field happens unexpectedly. So we're going to pick 1210 CFM. And across the top, you can see the outdoor temperature. So if you recall, the outdoor design temperature was 95 degrees. So with this information, I can determine that the design capacity, in this case, it's 33,200 BTUs per hour. So now the designer knows the design capacity of this piece of equipment. There's one last important step, though. So you'll see that there's a section called the sensible to total ratio. This allows the designer to calculate how much the total capacity will be removing sensible BTUs, which is the heat or the cooling BTUs, and how much is removing latent BTUs, which you can think of as the humidity in the house. Knowing that we have 75-degree indoor air, that sensible to total ratio is a 0.83. That means that 83% of our total capacity, 27,000 about BTUs, is for sensible. The remaining 17%, or about 5,600 BTUs, is for latent capacity. So we're going to now compare our design capacity to our load and see if it falls within the limits of ACA Manual S. So first we're going to make sure that per Manual S, the latent capacity exceeds the latent load. So this means that we are removing all the humidity with the size of the unit. And you can see here that we have 5.6 kBTUs capacity. We only need to remove 2.0 kBTUs per hour. Next, we make sure that our sensible is large enough. The sensible is 27.6, and then times that by the 95%, brings us down to 27,000 BTUs. The load was 25.7. And last, we want to check that the total capacity is not oversized. So it's less than the 115% limit of 33.4. And you can see here, 33.2 is less than the 115%. So with that, I'm pretty much ready to do the Manual S selection. It's a lot simpler because we're only talking through it in 2 minutes here, but this is essentially the process that we'll go through. In addition, we've already discussed how Manual S provides sinus limits for HVAC equipment. There's some other special cases, so if you're in high altitude or if you're in dry places, there are other things that will help you guide the process. The last part of the HVAC design is the Manual D, basic concepts. So the designer has already done all the calculations with heating and cooling for Manual J. They've already done everything they needed to with selecting the equipment with Manual S. Now they just need to figure out how to get the air into the room and using a duct system that will get that air that way. And so Manual D gives them the guidance on how to do this. So the basics that you understand, a fan uses power to move the air. The fan creates 2 kinds of pressure in the duct system, a static pressure and a velocity pressure. HVAC contractors can measure both in inches per water column. So given a constant amount of power, as static pressure goes up, velocity pressure goes down. And the opposite is true. So if the static pressure goes down, this means the velocity pressure goes up. So here's a list of things that can impact the static pressure. Supply ducts, supply registers, return grills, return ducts, the filter itself. All of these are adding on to the tool. So we have right now, after designing the duct system, a static pressure of 0.65 inches water column. And that's important because given any fan, the manufacturer publishes the total external static pressure that it can overcome. So it says how much static pressure is allowed to be there for the unit to operate properly. So now that you understand sort of the building science basics behind it and the static pressure aspect, the duct design process should be relatively easy. So the third step of the design process is the designer comes to the step with a lot more information already at their disposal. So they have the heating load for each room using manual J. They have the equipment selected, which means that they know the fan speed and fan setting. So there's only 3 steps left to the process. Determine the desired airflows, determine the friction rate, and then size the diameter of each ductwork. So go through quickly here. First, we determine the desired airflow. So you can see based upon the size of the rooms, the larger rooms have more airflow, the smaller rooms, loads, they have, smaller rooms have lower loads, the larger rooms have larger loads. And so this is the BTUs per room. We have 36,000. What manual D will help us do is associate the airflow from our system to make sure that we're meeting that requirement to keep the room comfortable. And so now we know how much airflow we need to deliver to each room. And so to do that, with manual D, we can set out the duct system. So here we see the equipment that's located in the utility closet that's starting off with 1130 CFM. And to get the air back to the equipment, we're going to have to go through a central return, which we have listed here. And so with this basic layout established, you can sum the airflow from each room to determine the airflow in each section of the duct system. So each branch will have the same airflow as the room. The lower branch will carry the sum of the bedrooms to the living rooms, so 565 CFM. And the supply line will need to carry all that, plus the bathroom and bedrooms, which sums out to be 1130 CFM. On the return side, for each CFM that fan supplies, we want 1 CFM returned back to the system. So the return also has to carry the total load of 1130 CFM. So now that we've determined how much air we need in each part of the system, we need to move on to the next step. So on the next step here is to figure out a metric called the friction rate. That requires 2 inputs, the available static pressure and the total effective. So the available static pressure is a value that tells us how much static pressure we have budgeted for the ducts. We start by using information from the manufacturer to determine the total external static pressure. Next, we worry about the total effective length. So if we just had simply straight supply ducts with 1 single return, it would be a really simple number. It would just be the sum of the supply and the return. If we just had 1 room, the total effective length would be 27 feet. But then I would just call it total length and not total effective length. So most duct systems are not just a single duct room. There are bends, there are transitions, there's different diameters, and there's multiple takeoffs from a single dock. So in our simple plan, we see we have 4 branch takeoffs. And each of these features imposes a static pressure toll. So you could say each of these features is effectively increasing the length of the duct run. So if the pressure loss for a 10-foot duct with a 90 degrees elbow might have a static pressure of 0.03, that's the equivalent to a static pressure loss of a 40-foot duct run, of a straight duct with no elbow. So in this case, 40 feet is the total effective length from the pressure perspective. Each elbow, each takeoff, each transition can be translated into an effective length of straight duct, and Manual D provides these values automatically within the software. So to determine the total effective length, you simply convert each of these features into equivalent effective duct lengths and allow it to have the actual straight duct length. So the design will go through this process for each of our 4 paths to calculate the total effective length so they can figure out the longest total effective length for the system. Here we see the total effective length of our 4 branches. So now we have 2 inputs, the available static pressure and the total effective length. The next part is finally simple. To get the friction rate, we just divide the 2, the available static pressure by the total effective length, and then multiply by, in this case, we get 0.12. So what does that number actually tell us? So the friction rate is basically a measure of how much static pressure you plan to lose for a fixed length of ductwork, hence the name friction rate. But an easier way to think about it is the velocity factor. So if your velocity factor is too high, then the air will move too fast when it leaves the duct, and this could cause noise complaints. And if the velocity factor is too low, well, then the air will be moving too slow when it leaves the duct, and this could cause poor mixing within the air in the room. So this is sort of intuitive. If we had half the available static pressure and our total effective length was twice as long, then our friction rate would be really low, and that doesn't sound good. So you can probably tell that the fan won't be powerful enough and the air will be moving too slow for these ducts. The opposite's also true. So let's say our available static pressure was twice as large and the effective length was half as much. See, now it seems like the fan is way too powerful. The velocity of the air is going to be so high, it's probably going to cause noise problems for the inhabitants. So we have a friction rate, we have a desired airflow, and the last step is the actual size of the duct. And so it's typically done using a duct slide rule. It often looks something like I have created a picture here. It allows you to dial in your friction rate with your airflow for each component of the duct system. So for example, for this particular branch, we have an airflow of 340 CFM, a friction rate of 0.12 inches water column. So lining these up means that I should have a duct diameter of 8 inches. So the airflow and friction rate actually allow each duct component, the designer, to repeat this process so that he has each duct sized properly. So I know I gave a lot here over the past 20 slides, but what we think the HVAC section does, it allows for systems to be right sized so that we have the right size of equipment going in. Then we're making sure that not only is it sized properly, but we're selecting the right piece of equipment. So even though it might say that we need a 3-ton unit, we know that we might need to go up to a 3.5-ton unit because of the manual S and the expanded performance data. And then by developing the ducts and designing the ducts in a way that properly puts the airflow through the house, we'll have a much more comfortable house for the inhabitants to live in. So finally, the last mandatory feature is water management. So the Energy Star water management requirements cover the several crucial elements for controlling moisture issues. So you think about water managed roof, making sure that we have a continual layer of moisture protection on the roof. Gutter and downspout systems in areas where that's needed to collect water away from the house. An extra layer of protection at susceptible spots, so valleys and penetrations. Making sure in cold climates that the eaves are properly protected. As we go down the house, as rain travels, the walls need to have a continuous layer of moisture protection from top to the bottom of the wall. A continuous drainage flame, which allows for properly installed flashing at the bottom of the walls, windows and doors. And then down to the foundation, making sure that a continuous layer of moisture protection that prevents water from moving from the ground into the foundation, making sure that we're moving moisture away from the home's foundation through proper sloping. And then the perimeter grain at the base of the foundation is to drain moisture in the ground. Lastly, building materials. So making sure that they're built with resistance to moisture damage and moisture-rich environments. So having the proper drywall and bathroom enclosures, for instance, and using materials with no visible signs of mold or water damage. So that's a basic overview of the major features we're looking for on the water management system. Each of these features are a requirement in code. So a problem that might occur during the process might not necessarily mean it's that trade responsibility. So leaky foundation might not be that the dam proofer did a poor job. It might be that the excavator didn't properly slope the house. A problem with the wall might mean removing the siding or replacing windows and doors. And if there's a problem with the roof, it might mean removing shingles or roofing materials. So these features are important to get right in every home, but they're especially important in an energy efficient home. Sort of some key points. The purpose of the checklist or the document itself is just to prevent moisture from causing those durability concerns to the home. Again, this is important for every home, but not just Energy Star homes. So what we found is that, providing these guidance and pulling all this information out from code and putting it into sort of a one-page guidance document has helped our builders really hone in on areas where there's the most issues and help them continue to build a better house. So to wrap it up and give a summary of Energy Star here, what we think is that, the biggest advantage to Energy Star is the powerful brand recognition. So from a sales perspective, having 85% of the consumers understand and want an Energy Star branded item is really helpful. And the Energy Star certification can help builders construct a better product and sell more homes. Version 3.1 and Revision 8 offer cost-effective and streamlined approaches. So version 3.1 in response to the 2012 and 2015 IECCs, and Revision 8, which is available for all of Energy Star, really take away a lot of the process flow issues that we're not adding value, just adding impediments. Be certified, verifying the energy performance and mandatory features of the house, and that making sure that all of the items related to the thermal enclosure and HVAC system are thoroughly thought through and planned out properly and then executed when the homes are built. And with that, I'll pass it back over to Brett.
Hey, thanks, Rick. Yeah, we've got some questions coming in here, and for those of you listening online, please drop in some more questions. We got a little bit of time here. The first one is kind of circling back to, I believe, the manual asks. Question from Rob. Why isn't the coil considered? The coil can be clogged or caked and can throw numbers way off and be a pretty, I believe, a pretty inexpensive fix.
And so the coil is considered, again, for the most part, the Energy Star program is on the new construction side, and in terms of protecting the coil, Energy Star requires a MERV 6 filter to ensure that doesn't become clogged and caked. And so from our experience, by putting in these new systems and then properly filtrating the system, we haven't seen that as an issue on the new home side as much. I'm not sure if there's another aspect to that question that I'm not properly understanding. But typically, with the proper filter and it protects the coil from becoming caked up with drywall dust and that aspect, and by sort of verifying that we have the proper static pressures, as well as by doing the static pressure tests, as well as duct sealing and duct blasting tests, we've found that has been sufficient. If there's more of your question, please feel free to send an email to me so I can research it further. But that's what I've seen, sort of from our partners across the country.
Thanks, Rick. Another question here from Todd. For duct leakage testing, how do the Energy Star 3 requirements compare to either 2012 or 2015 IECC?
Yep, so they're essentially equivalent at this point. 2012 and 2015, I believe, references for total duct leakage of 4%, 4 CFM 25. Energy Star version 3.1 has the same requirements of 4% total duct leakage that the 2012 and 2015 IECC. The only difference is in the 2012 and 2015, you're allowed to waive the duct testing if all of your ducts are in conditioned space, where Energy Star still requires that the ducts be tested if the ducts are in conditioned space, and to ensure that the total duct leakage is less than 8% in that situation. The reason that that test is still done for Energy Star, we would not want to have leaky ducts not delivering the air to the rooms that was designed to be delivered, as shown in the manual D portion. So it's still a requirement to do that test, regardless of whether or not the ducts are in conditioned space or not.
Great. Let's talk a little bit about how Energy Star can or cannot be used on existing homes.
Sure. So for existing homes, we have gut rehabs is the way that Energy Star can be used for a gut rehab. The issue that we've seen is that it's very difficult on the water management aspect to ensure that you're properly flashing around windows and getting foundation water issues in place. But we have seen it done successfully, typically in urban infill situations and affordable housing. So you can do it there, but it is a gut rehab so that you're getting down to the studs level and you know, going to Energy Star that way.
How about
there's also the Home Performance with Energy Star program. That's operated by the DOE, and that's for existing homes that aren't going through a substantial retrofit, a gut rehab retrofit, but it's an energy retrofit, and it requires a 20% reduction on energy use from software modeling. That's typically run in concert with utilities across the country. So utilities or state energy offices will have that as an option for those homes to receive Home Performance with Energy Star. It is a different certification than is available for newly constructed homes.
Does that require a HERS index rating for that software modeling, or is that anything?
It is no, it does not require a software HERS index rating for Home Performance with Energy Star.
What about mid-rise? So Energy Star 3 for homes can be used for low-rise, 1 to 3 story projects, multifamily. What about mid-rise or high-rise projects looking to use energy efficiency?
Yeah, so there is a Energy Star decision tree that shows how mid-rise sort of 6 stories and below can still use this Energy Star certification. For multifamily high-rise, there is a program for that, but it differs in a large way from this Energy Star certification process, where it's actually taking into consideration actual bill usage over a year before the home gets its for the building to become certified. So a year after it's constructed, you know, the home or the multifamily high-rise building is evaluated to see if it meets Energy Star specifications. But if you go to energystar.gov and search through multifamily, it will show you that decision tree, whether or not your house is eligible for the multifamily process or for the multifamily high-rise process or for Energy Star certified homes certification process.
Great. As far as this HVAC contractor checklist, and some of the items that need to be completed, it's my understanding that using ductless systems or mini-split systems may have a benefit. Well, you can set aside the argument or the debate on the performance benefit, but maybe the benefit as far as the paperwork goes. What's the difference if you're using some of these, duct-free systems?
Yep, so for a duct-free system, obviously, a manual D wouldn't need to be performed. And the commissioning aspect is lessened as well because you're not performing a static pressure test on a ductless mini split. So there is less in terms of the commissioning aspect that needs to be done. You still need to properly perform a manual J and manual S to make sure that even though typically when you see ductless mini splits and they're great technology, typically they have the ability to not just turn on and off, but oscillate with the amount of power they're providing to each room, so making sure that they're properly sized to meet the needs of the house. But you're correct in that there's not as much testing that needs to be performed, and it's mostly because the technology is too new. There's nothing that's been sort of standardized to ensure that those systems operate correctly.
Sure, fair enough. All right, Rick. Well, that's all the questions that we have here today. I really appreciate your time and ICF International for allowing you to do this with us. This session is going to be recorded and accessible. For those of you listening here live, please take a minute to fill out the survey that either has come or is coming your way. For those of you listening on demand, make sure to take your 10-question quiz for continuing ed to pick this up. And actually, one other thing before we wrap up, if everyone can see the resource, and I'll hand this out to those of you on demand, from the Building America Solutions Center. This looks like a neat little resource here that seems to go specification by specification for each point of the checklist, and kind of break down in imagery and step-by-step guides on how to meet each of these items. Rick, do you have any? Is this something you guys recommend from Building America here?
Definitely. So it's the BASC, the Building American Solutions Center. It's basc.pnnl.gov. And they've actually just updated all of their information to be Revision 8 compliant. So it references the Revision 8 checklists now. It has CAD drawings, good and bad pictures. It's a really great resource in terms of the wealth of knowledge and interactivity for getting that knowledge out into the houses that you're building.
Great. Yeah, so check that out if you're going to be taking a little more of a look. Otherwise, thanks for joining us, everyone. And thanks again, Rick. Everyone have a great week. Take care.
Thanks, Brett.